Good afternoon. This is the Black Belt track, and for the next two and last two talks, we will talk about orchestration, which means that for the next talk, some clusters, both swarm cluster and cube cluster, might have been hurt in the making of these slides. And parental advisory, there might be some cluster breakage happening in front of you at some point, so you might want to make sure that, how do you say, public something advised, public discretion advised or something like that. So the next speakers are going to be Stephen Day and Laura Frank. Laura Frank, who you might have seen in Austin, and if you haven't, I invite you to check the talk where lots of cluster were also hurt in the process, and cluster manager nodes and things like that. And they are now going to talk about a bunch of orchestration theory followed by a bunch of how does this map to actual cluster things. They warned me that it would be pretty dense and intense, and there was a warning I wanted to give before the previous talk, is that sometimes you can feel that there is a lot of content. Don't panic, that's okay. Remember, the talks are recorded, so you can kind of let go at any point and just enjoy the show with the confidence that you can catch up the replay later. And on that, please give a big round of applause for Laura and Stephen.
Thanks, everybody, for coming. This is container orchestration from theory to practice. So we've already been introduced. That's what we look like. Those are our GitHub and Twitter, well, our email and Twitter handles. If you have any questions, feel free to reach out. So today we're going to be talking a little bit about the reasoning behind the SwarmKit object model, and then Laura will be covering node topology and distributed consensus in Raft. So let's dive in. So a lot of this material is going to be oriented around SwarmKit, which powers Docker's swarm mode. A lot of this also applies to Kubernetes and any other orchestration system that you might have worked with, but all the examples will be with Docker swarm mode. So a little bit about how this looks after our big announcement yesterday is that Docker will be able to run both Kubernetes and SwarmKit next to each other, and that will be sitting on top of Containerd. So this is kind of similar to the slide you saw in the keynote, and just wanted to place this again so that you could see how it relates to everything else. So how was orchestration done in the before times, before we talked about containers, before we talked about orchestrators? Basically, you have some sort of, well, I have a dancing monkey here, but it could be anything like provisioning tools, sysadmins, what have you. And they're operating on their cluster, and then that cluster has some sort of output. And it worked up until a point, but it turns out there was a much better way, which was based in the Borg paper. So an orchestrator is basically a control system for your cluster. What does that mean? We have a bunch of letters and some fancy diagrams here. Basically, you're going to be taking a desired state input. You put that into an orchestrator, and that generates a set of operations that you apply to your cluster. And then your orchestrator observes those operations as the state S, and that gets fed back into the orchestrator, and it generates new operations to control your cluster. We can look at this from a functional view. And basically, we have the same function as we had in the previous slide, or same variables we have in the previous slide, but you're basically just running this function over and over again. And if you just sit down to code this, and you could actually simulate it in just kind of a Python script. But the issue is, many of these variables are hard to observe inside of a distributed system. So, for instance, like your desired state, you get directly from your user, but the state of the cluster you have to observe. You have to actually look at it and figure it out and discover it within your system. So what happens to actually control our cluster is we need to be able to observe what's happening with it, and this is the basis of the problem with cluster orchestration and why it's so hard, because there's things like node failure and that have low observability, and then there's things like user input that have high observability, and then things like process state, like figuring out whether a process or a container is running, which sits somewhere in between. And because of this variation in observability, it makes it harder to actually implement these things inside of a distributed system. So let's talk a little bit about how that connects to the SwarmKit object model and object models in general for orchestration systems. Basically, because of those requirements, because of this problem, our data model has these set of requirements. We need to represent the difference in cluster state efficiently. We need to maximize our observability. We need to support convergence of our cluster, and we need to do this while being extensible and reliable. So taking a modification on the old adage, show me your data structures and I'll show you your orchestration system. So let's take a peek at the data structures. In SwarmKit, we've organized it around a concept called services. Services essentially express a desired state of the cluster. It's an abstraction to control a set of containers. It enumerates resources, network availability, and placement, and it leaves the details of the runtime to the container process. In this diagram, we can see that we have 3 nodes, and there's 2 services, a blue and a green service, and we can see that they're distributed among our nodes. So this is a very kind of simple way of looking at the problem. And this is what we try to express with our desired state in the service data structure. There we go. So what does this actually look like? So this is the protobuf that's actually used within SwarmKit, and this is how we define it. It takes a few inputs. The most important is the task spec, and the task spec defines what you're going to run. So every single replica that you put inside of a cluster, when you actually scale it up, and I'll show this in a bit, we'll use that task spec to generate a new container on each node. And then the other parts will tell how to update and how to actually expose the service to the rest of the cluster. What happens inside of the orchestrator is there's an actual object, and we can see here that there's a service spec that we had on the previous slide. And what happens is that service spec is actually feeding back into our local status. And so what this looks like is this reconciliation loop where you have the spec, which has a desired state, feeding back into the object, which represents the current state. And I'll actually show that this model kind of works at every single layer of the cluster. So you'll see this at the service as a whole, and you'll also see this on the task part as well. So a little bit, I've been using this term task. What's it mean? It's a really overlaid term, but it's just a one-shot object within SwarmKit. And at the lowest level, it has 4 operations that include preparing. So during prepare, we actually do polling images. We set up network resources. We have a start method, which actually will start the container. We have a wait method, which will actually let you call. It'll wait until the task exit, and then a shutdown method. This thing isn't working. The arrows aren't working. Alrighty. 1 second. You have been signed out.
That is great news.
All right.
It should be fine.
It should be okay.
Oh. All right.
Can you hide the screen for a second? Or
this always happens when I'm in the middle of a video call or in the middle of giving a presentation at DockerCon.
Laura is demonstrating secure password management with 1Password.
Yeah.
If you're not using a password manager to manage your passwords, I highly suggest you use one.
Here we go.
And she has a good habit of making sure that she uses a password manager with all of her services. The next step here is demonstrating 2-factor auth.
Yeah. All right, Steve, we're back in business.
All righty.
Cool. It's every 30 days, by the way, that Google signs you out. So if you want to predict.
All right, where were we? Tasks, the task model. So this is the task spec. There's a lot of stuff on this slide, but basically it just defines a runtime, and that's how to run. So here we have a network attachment and a container. So tasks can do all sorts of things. Containers are just an implementation detail, really. And then it also defines how to restart it, how to place it, and then any networks that you want to attach to within your cluster. So this is the task, and this is kind of the meat of this talk right here, where we take the task spec and the desired state, and we're going to be feeding that back into the task status. And going back to our control theory diagram, this is what's happening inside of the orchestrator. And I'll talk a little bit about some of the challenges that come with this over the next few slides. So the task model the task is essentially the atomic scheduling unit of SwarmKit. This is similar to a pod. A pod is also the atomic scheduling unit of Kubernetes. And what they within SwarmKit, tasks are a one-shot operation, so they're pass or fail. They can't be restarted. And what happens is the orchestrator effectively sits there in a tight loop, and it generates tasks and puts those out to the scheduler to actually implement and ensure that your cluster is in the desired state. So Kubernetes has a parallel concept. This is the deployment struct that I've pulled out of the Kubernetes code base. And we can see we have a deployment spec, which is a specification of the desired behavior of a deployment. A deployment in Kubernetes is roughly equivalent to a service, kind of. But the same concept happens where you feed the deployment spec back into the deployment status. What does this look like in practice in Docker with Docker Swarm mode? Rather than in the past, Docker is very imperative. You run a thing, it fails, you run it again, and you're kind of interacting it with in a step-by-step manner. With Swarm mode or cluster orchestration systems, you can't really do that because you don't want to be woken up at night. You want to say, I want it like this, and then you want the orchestrator to ensure that the system is like that. So we do this by declaring objects. In this example, we declare a network. We call it. We declare that it's an overlay network, and we call it backend. Then we can create a service, and we can attach it to that network. Redis, of course, is the example service that one must always use. And then we can change the properties of that service by saying scale this. And the service that we created gets a random name here. So we say scale serene Euler equals 3. And then we can actually observe that with a Docker service ls command. So we have a demo. All right, so I have the very, very fancy demo tool that will show you our cluster state. We have 3 managers up here. And what we're going to see is, if I can get my mouse over the... So what we're going to do is we're just going to create a simple service. And we'll call it, it will be Redis, of course, for the demo. And so what we're going to see here is that we have one service. If we can see that, okay, it's a little small. I apologize for that. It popped out, and it was dispatched onto the manager 3. So that's not that interesting. Anybody can go onto a node and run a process, right? We can actually take that, and we can now modify that service in practice and change the declaration of that service, and we'll be able to scale it up to 3 nodes or three instances. And there we go. And then we need to actually say scale. There we go. And then it will, looking at our demo, we have 3 instances of our service running across 3 of our nodes, as promised. So now we have jelly. Let's move into consistency a little bit. Consistency is like declaring what your system's doing is very important. And remember we were talking about observability and controllability and how they're important. And part of that observability is consistency. So there's if we look at the data flow of flowing from a service spec like the input, which we have on the far left. Yeah, it works that way too. That is taken in by the manager, and then we actually embed that within the service object. And then when we hand down the tasks to a worker within Swarm, that task spec is then embedded into a task object, which ends up to be owned by the worker itself. Now, field ownership is a really, really important part of the consistency within SwarmKit. And the idea is that only one component of the system can write to a field at a time. What does that mean? So this is an eye chart, but look at the colors. The colors are very important. So on the left we have the actual message task, and then on the right we have the owner of that field. So we can see that different parts of the system own different fields. For example, the task spec is owned by the user, and the allocator owns the network attachments and endpoint fields. The interesting one here is the shared field, which is task status. And this is a little challenging because the task transfers from the manager into the worker. And if they're both writing that task status field, they could disagree. And we do this by making the actual state of a task a Lamport clock. And when that Lamport clock transitions from the manager to the worker, we know who's owning it. And this action is initiated by the manager. And so what happens is once the task is assigned to a node, it is then from that point on, the task is actually owned, the task state is actually owned by the worker. So that the manager, when it's trying to figure out the task state, it goes to the worker for that task state. This is what the actual task state looks like and the transitions that it makes. And so in the manager, you have it goes from new to allocated to assigned. And then when it actually gets onto the node, we have a set of pre-run tasks where it's preparing and it goes from ready to starting and then to running. And then we have terminal state, which means these are states that can never change. Once it gets into a rejected state or a complete state or a fail state or a shutdown state, that task is done within the system. So going back to this observability graph. So because we're using this field ownership properties and Lamport clocks, we can actually take task state and move it from kind of a low observability field into like somewhere in the middle. And using these techniques actually lets us do that. So I'm going to hand this talk over to Laura, and she's going to talk a little bit more about node topology.
Cool. Thanks, Steve. It was his birthday. So happy birthday. It was actually on Sunday, but because we're all so jet lagged, we decided it's really just the whole week. Because why not? So task management and the converging systems that Stephen just described are really just only half the fun. The cool part of using an orchestration system is that these tasks can be scheduled and dispatched across a cluster for highly available applications. So, of course, in order to enable this to happen, your cluster needs to communicate. So there are a couple different types of communication patterns that we need to have going on in our cluster in order for this wonderful converging orchestration system to be working just as we expect. I'm not talking about the mechanism of communication. That one's pretty easy to figure out, but the sequence and the frequency of communication. There are specifically 3 scenarios that are the most important to us and the ones that I'll kind of cover, some in more depth and some in less depth today. They're node registration, workload dispatching, and then state reporting. So reporting the status of tasks, as Stephen just shared, it's a kind of a shared field. So most of the approaches of communication between managers and workers or managers and the cluster take generally 2 patterns. The first is the push pattern, where the managers are pushing information down to the workers, and the second is the pull pattern, where the workers are pulling information down from the managers. Usually they're sending a payload, requesting something, and then getting a message from the managers as soon as the manager has that information to pass along. We can look at this a bit visually. Of course, this is sort of like a very, very simple worldview, so it's Really simplified, but still accurate. In the push model, we have a manager up there in the top left corner. The manager needs to communicate with the worker, but since the worker doesn't self-register in this case, the worker needs to, doesn't self-register with the manager, I should say. The worker needs to first communicate with some kind of discovery system. That way the manager can look at that discovery system, understand where the worker is, and then send a payload down to the worker. So that's the push model. The pull model is the model where the worker is kind of initiating the communication. They're sending a registration and payload up to the manager. They're asking for stuff. In most cases, they'll ask for something, and then the manager sends work or whatever the payload is back to the worker. So these, of course, have pros and cons, and in reality, most orchestration systems and most systems in general use some combination of both of them for many different situations depending on what the best fit is. So there's certainly, the push model is great because it provides better communication control rate. It also requires a discovery mechanism. On the other hand, the pull model is great because it's a little bit simpler to operate without that external discovery service in the middle there, but workers have to maintain that connection to managers at all times, and like what happens when that connection fails. So we can look at Kubernetes and SwarmKit and find a couple examples of these patterns in practice. For example, in Kubernetes, the manager will reach out down to the cluster for a couple operations, probably more than are on this slide, but these are the most interesting ones: fetching logs, attaching to running pods, port forwarding, etc. Those are all manager to cluster communication patterns. In SwarmKit, we also have the manager sending stuff down the pipe to the worker. This is work dispatching in batches, and we'll talk about that more in depth in just a little bit. And then the manager also sends the next heartbeat timeout. This is really important, and I'll tell you why when we get to rate control. But in SwarmKit, the worker is pulling a lot of stuff down from the manager. That connection is always open. The worker is self-registering with the manager. There are things like health checks, worker is pushing task status, and a bunch of other stuff that I couldn't fit on the slide, even though we're in like the hugest room, like a movie theater, still couldn't fit. So let's talk about rate control, because that's kind of the biggest problem that we have to solve when we're using that pull model, because that connection is always open, so we don't want the workers just being super chatty over the network and kind of overwhelming everything. So we can walk through a couple different scenarios of when rate control has been enacted or things are being controlled. So the worker sends a heartbeat message up to the manager and is like, "Hey, are you alive?" And the manager's like, "Yeah, I'm alive, and also don't ping me for 5.2 seconds." Because if the workers were just deciding when to ping and weren't getting any information from the managers, it would just be mass chaos. So this is also another opportunity for the manager to add a bit of jitter so that the pings are spread over time. You can imagine this is one manager and one worker, but what happens if you have like 20 or 50 or 100 or 1,000 connecting up to some number of managers? It can get pretty busy pretty quick. The other thing that's controlled in the SwarmKit world is workloads. So as I said before, the worker is asking the manager for work, and then the manager sends that workload down. This is done over a gRPC stream, and the manager can basically send data whenever it wants to for the worker. The interesting part about the rate control problem here is that the manager will batch the workloads, either 100 milliseconds or in batches of 100, whatever happens first. So we found this last night as we were waiting out in the cold for the buses to go to the DockerCon party. The buses weren't just leaving on some schedule, they kind of left as soon as it was full. On the way back, we saw that interval time, like time-based approach, where maybe the buses were leaving at 10:30 and then one at 11. Maybe they weren't full, but they were still going to stick to that schedule. If they would have filled up, they would have just left everyone there to enjoy the night a little bit longer, I guess. This does add a little bit of delay, but generally it's worth it because it's reducing the communication. At most, it's like 100 milliseconds, so it's really not super noticeable unless you have kind of really big problems to solve. So that's one thing that these two orchestration systems, and these two meaning Kubernetes and SwarmKit, have in common. And there's another thing that's definitely in common in a pattern that's repeated across many orchestration systems, which is the need for distributed consensus. So if we're running one manager and one worker, we can pretty much tell the state of the world pretty easily. What happens when you have 5 managers? How do we understand the state of the world and who's keeping track? And the who's keeping track is managed via the Raft consensus algorithm. And Jerome mentioned my talk from DockerCon US in Austin, and I give a lot more background on Raft, how it's used, different ways to like fiddle with it within your Swarm cluster. So I'm not going to go into so much depth. There are lots of really great talks about Raft. Raft is used in SwarmKit, and it's also used in Kubernetes. And it's literally the exact same code, and if you don't believe me, there's the path to the vendor directory in the GitHub repo. So it's coming from etcd. That's the most common implementation of Raft, and SwarmKit uses it. That's what Kubernetes is using as well. So what the important thing to note about this is that it's not Kubernetes making a choice or SwarmKit making a choice about things like leader election, log replication, split brain election cycles, all this stuff. It's Raft. So they're just simply implementing the protocol that's already been defined for them, which is why a lot of these patterns are repeated because they're using shared components. If you want to know more, please check out Secret Lives of Data. This is a website by the original author of Raft, or at least one of them. I highly encourage you to check that out, learn more about Raft. You can go through log replication, leader election, etc. Later on in the talk, I'll have a little Raft note on things that are really not up to SwarmKit or Kubernetes, but are relying on the Raft protocol. Like I mentioned, this Raft log, which is what it generates, is the single source of truth for your application. This is how distributed consensus is managed. When I'm talking about a log or a Raft log, I'm not talking about centralized logging or application logs. I'm talking about the time series ledger source of truth append-only log that holds the state for your application. In Swarm, they live in varlib docker swarm. They're living in varlib etcd member. Then there's a couple directories in there. So same deal. The cool thing is that they're pretty easy to observe and even read. There's some cool stuff in there. And one of the things that's really important, and just for the sake of time, I'm going to scroll up to the cheat version of the demo that I already did. It's storing the Raft Index. So this index is representative of the election cycle that the Raft consensus group is on. This election cycle changes when managers are either elected to a leader, maybe a manager goes offline, and new election cycles have to be voted on and agreed upon. Everything that's in this Raft log is the result of a quorum right, which means that your managers have to be online, voting, and agree that the action can take place before ending up in this log. This is important because when we get to things where there may be a dispute or we're trying to figure out what is the real state, this is going to be the single source of truth. There's a super cool tool in SwarmKit called Swarm Raft Tool. It's in the CMD directory, just in the repo on GitHub or in the Go project, where you can look at the logs, the Raft logs. You can also use this tool called SwarmCTL to look a little bit more in depth into what Swarm is doing behind the scenes. Cool. So let's take it back to manager worker communication. And I want to talk not necessarily about the styles of communication or communication patterns, but some kind of real life examples of what happens when and how the workers and managers are talking to each other. So like I mentioned before, the worker is able to connect to any manager, and it opens up this connection, and it's kind of open all the time. There are 3 different types of states for a manager to be in. One is leader, which means you're the leader of the Raft consensus group. There's a follower, and then there's dead. So we don't really care about the dead because they're either trying to come back online or being replaced, or there's a new leader election cycle happening. What we care about most now is leaders and followers. In the case that the worker is attached to a follower, the follower is going to forward all of that traffic to the leader. In the case that there are many workers attached to a single manager, which in production, this is the most common case that you have more than one worker, if you're running something in production on Swarm, which I hope you have more than one worker if you're doing that. The cool thing is that the follower is going to forward, multiplex and forward all of those requests, so it's like a single connection. So if you can imagine a cluster with, I think the example down here is 10,000 workers, and 5 managers, then each worker is responsible for about 2,000 connections, but each of those followers will forward 2,000 connections worth of stuff to the leader. So it can greatly reduce the network load by spreading it out a bit more evenly. This is a part where Raft comes into play. So what happens when a follower manager is forwarding traffic to a leader that goes offline? So the new election cycle is going to kick off, and that's Raft. So that's really not SwarmKit making up some rules about what should happen. That's coming directly from Raft. What's important to know is that the managers will start redirecting traffic as soon as that new leader is elected. So that looks like this, and hopefully we can get our manager back, which luckily, because I made these slides, we do have one back in the next slide. The manager is able to, or I'm sorry, the worker is able to connect to any manager, and the reason it can do that is that the worker has all the information in it, like the worker has the information itself about the addresses of the managers. So if a manager fails, that worker can just simply reconnect to any random manager because it has the addresses of all the managers in the manager cluster. Cool. I want to just do a quick demo because this is a lot of theory, and we want to just see this working as it should. And I thought a cool way to illustrate systems working as we expect is to break them and then watch them recover. So we talked about convergence, and we talked about the cluster being smart enough that the workers can kind of reattach to other managers, and the managers can handle themselves with the Raft consensus. So what we should expect if we just go in here and delete one of these nodes is that in just a couple seconds, because this is a node app and takes a little bit of time to refresh, but we should see Swarm understanding that, hey, the state that's declared is not the actual state. So we have this, manager is offline, and then we should see that little task coming back up. So this is all of the theory that we just discussed kind of in practice, in kind of admittedly a bit of an underwhelming example, and that's sort of the whole point, is that all of these hard engineering problems are solved for you and wrapped in a really, really nice user interface. Whether you're using Swarm or whether you're using Kubernetes, you have access to these really complex orchestration problems that are solved for you already, and what you get is a really nice application that's highly available and stays offline, or online, sorry, it doesn't stay offline, even when you do some bad things. I'm gonna lose quorum just to see everything fail and blow up in the worst way. We should see red. Quorum is also very important. I didn't talk about that in this talk, but check out Secret Lives of Data and you'll learn more about it. Cool, so I just demoed a bit of bringing some nodes down. In this case, we had only managers in our cluster for educational purposes. In reality, we would have a mix of workers and managers. But how does their state get managed, and who's responsible for understanding the up and down state? So even if you are using Kubernetes with Docker, as was just announced yesterday, Swarm is still handling the node management. So this up-down state and node management is still handled by SwarmKit, even if you're going to deploy to a Kubernetes cluster. And I think that's one important distinction that maybe didn't get absorbed fully yesterday, is that SwarmKit's not going away. It's still a really important part of the Docker EE, Docker for Mac, running clusters with Docker experience. The manager leader, not one of the followers, is responsible for committing worker state up and down, or unknown in case that it's not reachable and we haven't quite figured out if it's up or down. That state is committed in Raft and is propagated to all of the other managers. That means it's recoverable in case that leader goes offline or there's some leader re-election happening. The cool thing that SwarmKit decided to do is to hold those heartbeat TTLs. So I mentioned there's this ping pong going back and forth between worker and manager. Those are kept simply in manager leader memory. So it's super fast. Otherwise, every ping would result in that quorum write that goes in the log and is replicated across the manager group. It takes a super long time, and then your managers are just too busy voting to get anything done, and no one wants that. There's a couple other failover scenarios about moving to unknown, waiting for them if they're up or down. Some of these things are happening and also very observable, so I won't go into too much detail for the sake of time. Consistency is also another problem that needs to be solved, especially when you're running multiple workers, multiple managers. And one way that this issue of consistency is solved is with the sequencer. So every object in the store has a version field, and this version field is the Raft Index. And like we just saw in the demo earlier, this Raft Index is referencing the election cycle of the time that the object was last updated and committed to the Raft log. The updates in the SwarmKit are versioned, which means you have to provide some version. And we can maybe look at this visually. It's a little bit easier to understand, although the concept is not super difficult. So if we have version 189, which is the Raft Index of when it was last updated, and we have an update request, and we say the current version that we have is 189. I want to make some update. In this case, we're updating the image. That's totally fine, because you have the current version, and then that version is going to be incremented. The bad path is what happens if you make a request to update, and the version that you think is the current version is actually outdated. That is going to be rejected because we know it's out of date because we have that index. So this is different than the Lampor clock that Steve was describing earlier. This is the Raft Index, although very similar concepts. So if you want to check out these projects that are open source, you can check them out on GitHub. There's SwarmKit, etc. Of course, Kubernetes is free to check out as well. I would highly encourage you to also check out Secret Lives of Data and get to learn a little bit more about Raft because it's super important for orchestration systems. That's all that we have, and we have time for questions, thankfully. So thank you very much.
If you have questions, a reminder, there is a mic on front in the middle and on the sides on the middle altitude of the room. Questions? There should be a mic really close to, yeah. Oh.
Hello.
Oh. Hello.
I'd like to ask about the unknown node states. Is it possible to have, or how do you behave in partial node failure scenarios? So can you end up in a situation where you have a task scheduled to a node, but the manager considers that node to be offline, but that task is actually still running on that node? Do you end up in a situation where the master decides to schedule a new replica of that task onto a different node, and then you end up with two duplicates of the same task that are running?
Yeah, it's is my mic on? Yeah, it's possible. So we opted for the behavior such that we don't kill any running tasks from the perspective of the worker. So if there is if the worker loses contact with the manager and it's unable to update that state, we won't kill those running tasks, because you can't tell the difference between whether there was a complete loss of quorum and a loss of manager, or whether you're just having connectivity problems on that single node. So you don't necessarily want to kill those working tasks, and it's a trade-off between the property that if you lose quorum, you want your app to remain up, right? So by not killing tasks in place when that condition happens, you can keep your application running and then recover quorum in that time, and hopefully recover. But that's not to say you could have a configuration in an orchestration system that could let you choose that behavior under ultimate failure.
Yeah, I think the important point is that when you lose quorum, whatever is running stays up. Decide what that means for your application. If you're running a web app, that's fine. But what can't happen is that your system can't converge. So if stuff goes down in the time that you lose quorum, then those are toast until you can regain quorum.
Yeah. I think you answered the question for the case of master failure, but I was talking about partial worker failures.
They're from the perspective of the worker, you can't tell the difference, right? You can't tell.
But I mean, if the worker control loop stops working, but the containers are still actually running.
So if the worker loses connection to the manager, it can't receive instructions. So it's now split brain from the rest of the system, right?
Yes. And in that situation, will the master schedule a duplicate instance onto a different node?
Yes.
Yeah.
Yes.
After a heartbeat time that you can configure.
Yeah. Thank you.
I have a question on the, in cases where you have multiple swarm clusters, is there some work going on joining them into, if we have in distributed clouds or something, is there some work going on?
Are you talking about federation?
Some kind of federation?
Federation? Not currently. We've looked into it a little bit, but if it's something people would be interested in, we should raise that. So it's a slightly different problem than a single cluster orchestration. So,
but it can be assumed that with a high network latency, you can trust having masters in different places, I guess.
Typically not with Raft. Raft, it doesn't really work well under high latency situations. So you need to do, you need to use a much different architecture, which can let you better handle that situation.
Okay.
Yeah, keep your managers in the same AZ or region, whatever makes the most sense, but not multi-region. Raft is
a
little slow.
You can run it cross AZ if the latency is really low, but definitely not cross region.
Yep. And if you're going to run it cross AZ, make sure you plan that one data center is going to go up in flames and place your managers in a topology-aware fashion so that you don't lose quorum if that happens.
Yeah.
In case of split brain with the masters, is there any recovery scenario available?
Yes, Raft handles that very elegantly. And actually, there's a really, really good example on Secret Lives of Data that goes through. So basically, the Raft log that we talked about has the log entries have basically two different states. One is committed and uncommitted. And a Raft log can be propagated to the manager or to some managers that respond without being committed until the votes come in to say, yes, let's commit it. Because so what happens is sorry, we're going into the break, but I hope that's fine. If you're in this room, then you're interested in Q&A. So I can just show you the demo of this. I own demo.consensus.group because I have a problem with buying domain names. Let's speed this up. This is leader election. Cool. So this is exactly that case where we're in election cycle 2. And we've lost quorum. We have only 2 managers online. And we can see that, and maybe it's a little hard to see, but these logs are in an uncommitted state. So they have the little dashed line. And they're not going to actually be committed until there are enough votes coming in from the rest of the managers. I'm going to slow this down a little bit. Maybe not that much. So we can see that manager, like S1, which is the leader because it's red, has gone out to S2 saying like, hey, are you cool with this? And S2 is like, yeah, cool. It has it uncommitted in its own Raft log. It's going to update a couple things, but it doesn't have quorum, so it can't actually commit these logs. Until now we have quorum. We can now start one by one committing these to the Raft log because we have enough votes to say, yep, that action is permitted and it can take place. We also have, so that's like the ideal way that Raft logs go from being uncommitted to committed, but there are also inconsistencies and opportunity for inconsistency. So in this case, we have 2 uncommitted logs from election cycle 2. We've already moved on to election cycle 3, which means we have inconsistencies. This can be a result of many different failure scenarios. What will happen is that now that those that those managers are online, we'll kind of reconcile the state up until the committed point, up until the ones that are solid. But now we have different entries that differ from the last leader that was online. And this is where that Raft Index and that kind of version number is really important because 3 is greater than 2, so 3 is always going to be respected in that case. And that's handled by Raft in the way that it kind of repairs inconsistencies for us for free just by using the protocol. It's built in. So, cool. I love that demo. It's my favorite.